Hello! In this video, we are going to prove the following theorem. Suppose G is a group and A is an element of G. Then the given set is a subgroup of G. Now, since G is a group, this means that G is equipped with a binary operation, such that G is closed under that binary operation. Associativity holds. G has an identity element, and every element of G has an inverse. Now, if A is any element of a group, then we denote the inverse element as A with a superscript of -1. Now, the general notion for integer exponents for elements of a group is as follows. A to the power of 0 is just the identity element of the group, and A to the power of a positive integer exponent tells us the number of times we are multiplying A by itself, while A to the power of a negative integer exponent tells us how many times we're multiplying the inverse of A by itself. Now, in previous videos, we gave a more careful description about how integer exponents work for elements in a group, and we were able to prove the following properties. Given any group element A to the power of m times a to the power of n is equal to a to the power of m plus n for all integers m and n, and a to the power of m to the power of n is equal to a to the power of m times n for all integers m and n. Now, to prove that this set is a subgroup of G, we are going to use the one-step subgroup test, which tells us the following. Suppose G is a group and H is a non-empty subset of G. And suppose for all x and y in H, x times the inverse of y is in H. Then H is a subgroup of G. Okay, so now let's get into proving this theorem. To start on the proof, let's give ourselves a group G with identity element E, and let's let A be an element of G. From here, the goal is to show that this set is a subgroup of G, and we're going to show that using the one-step subgroup test. Now, first, let's show that this set is non-empty, because that is a requirement for the test. But it's pretty clear that this set is non-empty. All we have to do is choose any integer, and then a to the power of that integer is an element of the set. For example, if we choose the integer 0, then a to the power of 0 is an element of the set, because a to the power of 0 fits this form. And so that confirms that the set is non-empty. So now, let's show that this condition is met. To do that, let's give ourselves two arbitrary elements, x and y, which belong to this set. From here, the whole goal is to show that x times the inverse of y belongs to the set. Now, since x and y belong to the set, what that means is that x and y are elements of G with this form. In other words, we can say that x is equal to a to the power of p for some integer p, and y is equal to a to the power of q for some integer q. So now, let's multiply x times the inverse of y. Now first, we're going to substitute x for a to the power of p, and we're going to substitute y for a to the power of q. Now, according to this rule, we can just multiply the exponents here. So this gives us a to the power of negative q. And then applying this rule, we can just add the exponents. So this gives us a to the power of p minus q. And a to the power of p minus q is an element of G of this form. Because p minus q is an integer, we have a to the power of some integer. So this must be an element of the given set. And so this shows that x times the inverse of y is an element of the given set. And so that verifies that this condition holds. And so by the one-step subgroup test, we can conclude that the given set is a subgroup of G. And so this completes the proof. Now, we have just shown that this set is a subgroup of G, and we often refer to this as the subgroup of G generated by A. So yeah, that's pretty much it for this video.